the topic of my today's talk would be not only today's talk, but also the full set would be functorial definition of quantum field theory. So if you know everything, I can give you this definition. So quantum field theory is just a symmetric monoidal function from category of geometrical enriched cobordism to tensor algebra. So here I sit down and that's it. So if you are a supercomputer, you can say, okay, I know what quantum field theory is. However, for ordinary people, I need to explain what do I mean. So I have to explain what category is, what functor is, what does it mean to be symmetric monoidal, what does it mean to be geometrically enriched cobordism. Okay? So somebody has some noise. Okay, how can I see who has this noise? I have an idea. So I think Shangugo has extra noise. But I cannot do anything. So, YMSC, may you just stop noise coming from Shangugo. Sorry, no teaching assistant this time. Nobody wanted to be a teaching assistant. But I'd like YMSC to switch the sound of Shangugo off. Okay. Okay, thank you. So what I'm going to explain first, what do all these notions mean? Second, examples. And you will see that conventional quantum field theory is an example of functorial. In particular, Dirac quantum mechanics is exactly functorial QFT. And then we will come to more complicated examples. More complicated and interesting examples. And along the way, we need to answer the following questions. First question A. Where is H bar? There is no H bar in this definition. Question number 5. What the field? There is no field in this definition. Okay, Shangguo, may I ask you to switch off your microphone? Okay? Or may I ask organizer, who is YMSC, to switch off the sound of Shangguo? Okay, nevertheless, it's hard to take me out of track. I will continue. So here are the main questions that I'm going to discuss. So, point number 1, category. It is set of elements called object.
Andrei Semenovich, someone asked you in chat.
Okay. 1 second, thank you. Okay. So everything is possible. Thank you very much. Let me try to see how can I improve it. So, Maxim, is the board okay now?
I think yes. All right.
So please help me giving me this back reaction. So here is set of elements called morphisms. each morphism has a source and target. So source belongs to objects and target also belongs to objects. So actually this morphism is the union over alpha beta of morphisms alpha beta. So alpha is a source and beta is a target. And third thing, composition. Mu. It's a map. Morphisms alpha beta times morphisms beta gamma to morphisms alpha gamma. And it takes M alpha beta, M beta gamma to what is typically called mu alpha beta, mu beta gamma. Now, axiom. Composition of morphisms is associated. So M alpha beta composed with M beta gamma composed with M gamma delta equals M alpha beta composed with M beta gamma composed with M gamma delta. I may put another axiom. Existence of one that belongs to more or up or id that belongs from morphism to alpha alpha for all alpha such that id M equals to M and also M id equals to M. So if you try to imagine this structure, you may say if objects has only one element, then category is just a semi-group. Okay. So this definition is a precise mathematical definition. But mathematical physicists like to have examples. I'll call it definition. Example number 1. Subsets of some set U. So objects are subsets V inside U. What is the morphism? For two subsets V1 and V2, morphisms from V1 to V2 form empty space if V1 is not inside V2. Morphisms from V1 V2 is something that is called V1 in V2. It's an element. So this is a one-element set if V1 is inside V2. Okay? Now associativity is clear. V1, V2, this morphism composed with V3 equals, okay, I will write it like this. V1 in V2 composed with V2 in V3. So I'm writing composition of morphism is V1 inside V3. Associativity is obvious. So this is example from set theory. Maxim, how is the video?
All right yet.
All what?
All right.
Okay. Very good. Let me consider example number 2. X BS objects are sets, not necessarily subsets, but just sets. All sets. Morphisms maps are sets W. Morphism W1, W2 maps from W1 to W2. Composition of maps. Okay, one can check associativity. Now, let me go to example number 3. Objects are linear spaces that I will also call, okay, I'll call them L. Called L. So when I say linear space, I mean linear space over the field. Let it be over C. And I call them L. Like L would be just C to the power N. Morphisms. Morphisms. L1, L2. Linear maps from L1 to L2. And composition would be just composition of maps. So such category is called linear algebra category. You can understand morphism as N1 by N2 matrices. And composition is just multiplication of this matrix. So it is linear algebra category. Let me fix N. And consider subcategory of linear algebra. That would be endomorphisms of Cn. It is a semigroup of N by N matrices. Invertible morphisms of endomorphism of Cn. It means the determinant of corresponding matrix is non-zero. Form a group known as GLN. Okay, so here are examples of categories. Let me give you more examples. So this linear algebra category is something that appears in the quantum field theoretical functor. I have not explained you what the functor is, but I said that there will be tensor algebra. So tensor algebra would be a category that is obtained from linear algebra category when we add an extra operation. But before I will add this extra operation, let me note that I will use it heavily. I mean this example. And let me consider another example. Example number 4. Consider a graph I would even call it an oriented graph. Oriented graph. So we know what the graph is. Set of vertices that I call V alpha, V1, V2, Vm. And also set of edges. So let me consider the following graph as an example. V1, V2, V3, V4. And now there is a category of paths on the graph. First, each edge is a path. So this is a path. Second, collection of edges starting from V phi alpha and ending on E beta is also a path. I want to put here this quotation mark.
Semyonovich, there is some question in chat.
Thank you. Thank you very much for helping. Yes, there is no edge connecting V1 and V3 in this example. No edge. However, there is a path. So, you see, this is informal understanding. That path is something that you go along edges. But this is for physicists. For mathematician would say that path from V alpha to V beta is a minimal set such that first edge belong to path V alpha V beta. Second, path V alpha V beta and also edge V beta V gamma, this collection belongs to path V alpha V gamma. So mathematician, pure mathematician, would give this definition. But what people actually mean that you can walk along the graph. And then it is clear that let me write it here. Paths form a category. Whose objects are vertices. In particular, there is one path from V1 to V back to V1 like this. There is another path like this. And if I go twice, it would also be a path. Okay? But examples are just illustrations of this concept. And it is absolutely clear. Exercise. Check that composition. That is, oh, it's obvious, not an exercise. Form a category. Objects morphisms are paths. Morphisms V alpha V beta are paths from V alpha to V beta, and also composition. When I have path V alpha V beta, then I write comma, and here I put path V beta V gamma. This set is a path belongs to paths to paths from V alpha 2V gamma. And it is obvious that this composition is associative. And this path would be generalized to cobordism. Okay. Now let me check the time. So my rule is that I will talk 45 minutes and then I will do a 10 minutes break. Okay, sometimes it would be not 45 minutes. Sometimes it would be 47 minutes, but no more. No more than that. And then there will be a 10 minute break. During the break, it would be possible to ask questions. So now I am very close to the break, but still I need to say something else. So if you have a question, please ask.
In the second comparison, what space is
I need to explain what functor is. Given two categories, A and B, the functor is a map that does the following. It maps objects of A to objects of B and also morphisms of A to morphisms of B, such that so I will call it alpha is going to F of alpha. M alpha beta is going to F M alpha beta. Okay, I don't want to write morph. Let me write this more. Okay. More alpha beta. And this belongs to more F of alpha, F of beta. Such that F applied to combination M1 alpha beta composition to M2 beta gamma equals to F of M1 alpha beta, and here is composition with F of M2 beta gamma. So this thing belongs to morphisms between F alpha and F gamma. Because this thing, let me write it like this. This object, this thing belongs to morphism between alpha and gamma, and F applied to this belongs to morphisms between F of alpha, F of gamma. Now here, this thing belongs to morphisms between F of beta and F of gamma. This thing belongs to morphisms between F of alpha and F of beta. And here I have composition in the space of morphisms of the category B. And this, of course, belongs to morphism between F of alpha, F of gamma. So this is a mathematical definition. So it means the following. It means that application of the functor preserves composition. It preserves composition. Example. So let me consider the simplest example. Let category A contain just one object. Then it is a semigroup. Let category B contain also only one object. Then it is another semigroup. So what does this axiom mean? Axiom of being a functor means just homomorphism of semigroups. Just this. I'm sorry for being too mathematical, but I will hope that physics would come in example. Okay, so I will do like this. I will give rigorous definitions and explain what does it mean in example. So I think, yes, for exactly 45 minutes. So now we are close to the break. I actually need questions, and of course, I would like to see you. So if it's possible, just show up. So, and as you know, I really like questions. So let me ask Maxim. Maxim,
Yes, I'm here.
was it understandable?
All is clear.
Okay. So if there will be no questions, let me go for a break. And the break would be exactly 10 minutes. So we would start at 2 minutes after exact hour. Okay? So we discussed here the concept of one second. Okay. So let me continue. So functor, if you wish, is some kind of analog of homomorphism. So morphisms are like elements of the group. And functor is something that preserves composition. So later on, probably tomorrow, I'll give you a lot of other examples of functors. Let me give you another example of category. Of category. It's called Cobordism. So what does the word Cobordism mean? It actually means the following. Suppose you have as X, it's a space with a boundary. And just imagine that boundary has several components. It's an example. So this is X. Here is gamma 1, gamma 2, gamma 3. I would like to declare gamma 1, gamma m incoming, boundary component. And in this example, let me gamma 1 and gamma 2 be incoming. And I will draw it like this. Incoming. And let gamma m plus 1, etc., gamma m plus n would be outgoing. Boundary components. So I will denote it like this. Okay, and then I will say the following. I imagine that X is smooth manifold. I will consider that I will define a new category. Objects of cobord category are spaces Y. Not necessarily connected. Morphisms are spaces X real dimension such that boundary of X is Y1 and Y2. Let this be Y1. In this example, Y1 are two circles, 2S1. Y2 is just a single S1. And this X belongs to morphism between I1 and I2. So you see this cobordism look a bit like paths on the graph. Okay? Of paths.
Why we consider real dimension?
Because the concept of boundary implies that we study real manifolds.
Okay.
But you are asking a very proper question. And this question is, could we invent something like complex cobordism? And what would this possibly mean? It would not be about a boundary. So you see in the word cobordism, this board and boundary have the same root. Okay? So here important thing is that y1 and y2 are boundaries of x.
There is some question about orientation, chat.
Okay. So I would do it like this. Let x be oriented. Then I would like to say that I will take y1 with, sorry, y in with one orientation and y out with another in the following sense. Orientation on y1 is given by the basis and the tangent space. When I'm drawing an arrow like this, I can form a basis in the tangent space to a point in x. And when I draw an arrow in this direction, clearly orientation on y2 together with this arrow you see this situation is different from this situation a bit. So if you consider induced orientations, then induced orientations on y are opposite. So how to say it properly? So probably the best example would be just to consider cylinder. So if we have incoming something, I put it like this. And orientation is like this. If I have outgoing something, then you see I'm just trying to show that orientation is opposite. So orientation is made out of orientation on a boundary and orientation of in or out vector. This. Okay, I will, you see, when I'll explain the full story, okay, I'll come to this issue of orientation a bit later. Now I just want you to see the full picture. I just want you to see that these cobordisms are just kind of analogs of paths. Okay? So, what do I mean that they form category? So these are objects, these are morphisms. So what is the composition? composition. X1, X2. X1 composed with X2 is X1 union X2. So here I have Y. So these two circles form Y in. This is Y middle. And these three form Y out. So X1 belongs to the morphism of Y in Y middle. X2 belongs to morphisms of Y mid, Y out. So in this example, Y in is Y1 and Y2, Y out is Y3, Y4, Y5. So this would be Y1, Y2. This would be Y3, Y4, Y5. And this is Y middle. And X1. And in this example, X1 composition with X2. That is X1 joined X2. Belongs to morphism between Y1 and then Y2 and Y3, Y4, Y5. Okay? Okay. This was mathematics. However, just imagine for a second that you are a mathematical physicist. So what you can see on this picture? On this picture, you see the process of closed string scattering. We have two incoming circles. They come together, form intermediate string called Y middle that later on decouples into three final strings. Okay? Okay. Now, what do I mean by saying that this composition is associated? I mean something like this. Just imagine that later on, I will glue these two circles and these two circles together. Then on this picture, I see X1 joined X2 join X3. That could be written either as x1 join x2 join x3, or x1 join x2 join x3. So it is associativity of composition. That's why cobordism form category. Now, what else I used in the definition? What is geometrically enriched cobordism? So some people consider x1, x2, x3 just as smooth manifolds. However, to make geometrical enrichment, we take a local field on X. What is a local field? Like metric, complex structure, almost complex structure. One form, scalar field. So people mostly use metric. So I will speak about metrics. And consider metrically enriched property is a pair X and G, where G is nothing but metric on X. Now, what about composition? So here we have x1 and metric g1. Here we have x2 and metric g2. If I have x1 with metric g1 and x2 with metric g2, I can glue them together to get x1 union x2 with the metric g12. So g12 has the following property. The g12 restricted to x1 is g1, g12 restricted to x2 is g2. So this is how I can geometrically enrich cobordism. Okay? And here we are coming to the following thing. Let me forget for a moment. So what I'll forget for a moment? The words symmetric monoidal. Let dimension x be equal to 1, and let me consider only connected axis. So what are cobordisms? Are just intervals. This is y in, this is y out. Now, I have this simple category. So geometrically enriched means that I remember length of an interval. T. Now, I'm studying the functor from cobordism to, I say, tensor algebra. But now it would be enough to study functor to linear algebra. So objects that would be points would go to vector spaces that I will call. So how did I call vector spaces? L. Then morphisms, intervals. They would go to morphisms here. So since I have basically the same point, it would be just endomorphisms of L. Now, intervals enriched with metric it would mean that intervals enriched with metric should go to endomorphism. So functor takes values in endomorphisms of L times functions on R plus. What is this R plus? Length. So to compute the value of the functor on an interval of length t, I need to substitute this length t here.
Andrei Semyonovich, could you turn your camera to right part of the desk, please, at moment? Thank you.
Like this?
Yes.
Now, let me call functor f of t. Denote, let me denote. It belongs to endomorphism of L times functions on R plus. Now, the main operation is here I have T1, here I have T2. This is X1, this is X2. The operation is joining two intervals together to get a new interval. So this is composition. So I have a functor if f of t1 composition with f of t2 in endomorphism equals to f of t1 plus t2. So here is what I mean by functor from geometrically enriched one cobordisms to linear algebra. Because I consider only one object, it's a point. You see, these fancy mathematical words come down to the very simple equation. So what do I know from this equation? First, f of 0 equals to 1. Okay? Id, identity. It's okay. Then the question is, how to solve this equation? So Maxim knows, but let me ask other people, how to solve this equation?
Exponent.
Yes, you know. F of t equals exponent th, where h belongs to endomorphism of L. And this is nothing but Dirac quantum mechanics. That is how it comes out. Okay. So now let me say something about monoidal structure.
That Kypros is in fact female because
Sorry? So if you say something, say it louder. Monoidal structure. Monoidal structure means that you have extra operation. That I will call like this. On objects and on morphisms. Instead of giving definitions, let me try to explain to you what do I mean. Linear algebra. If you have two objects, L1 and L2, two vector spaces, then you can form L1 tensor L2 that is just L1 tensor L2. So this monoidal structure is just tensor product. So what is the tensor product on morphism? Morphism between L and L prime is nothing but an element from L star times L tilde. That is what the morphism between L and L tilde is. So space of morphisms is like this. Now, what can we say about the space of morphisms between L1 tensor L2 and L1 tilde tensor L2 tilde? It's enough to study this. So it's very easy. These are elements of L1 tensor L2 star tensor L tilde. So here we have just L1 star tensor L2 star tensor L tilde. So what kind of axiom may I use here? Okay, let me put here L1 tilde tensor L2 tilde.
Excuse me, Professor.
Yes?
I didn't hear that. What is L star?
L star is dual space.
Okay,
It's a standard notation. L star is a space dual to L. It's a standard definition in linear algebra. It's a space of linear functions on L. Of linear functionals on L. So people study it immediately when they study linear algebra. So I decided not to define it. So morphism between L and L tilde belong to this space. So what is the morphism between the tensor product here and tensor product here? It is something like this. But I can rewrite it as L1 star tensor L1 tensor L2 star tensor L2. So this is the space of morphism between L1 and L1 tilde. And here I have the space of morphisms between L2 and L2 tilde. So I define this cross, or it's called monoidal operator on objects. And let me see what happens on morphism. I just want to say that morphisms from L to L tilde. So there is an operation on morphisms that is compatible with this process. So morphisms between tensor products, okay, between monoidal products, morphism between monoidal products is the monoidal product of morphism. I will come to it in more detail later. But here, I just want you to touch the full definition that this is this monoidal structure in linear algebra. And if we say that we have linear algebra with tensor product, it is called tensor algebra. Now, on manifold, what the star could be? Y tilde is just a is just this. Disconnected, it's called disconnected sum. So let this be Y, this be Y2. And I have this structure. So this is the world where I have only Y1. Tensor the world where I have only Y2. Gets. So here I have the world where I have both. Okay? So this is monoidal structure on objects. But there is also monoidal structure on morphism. Suppose I have y tilde, and here I have x1, here I have x2, And you see the cobordism between monoidal product of y1 and y2 contains this monoidal product of cobordism. Exactly like it happens in the linear algebra. So I just mentioned you this monoidal structure. Okay? I just mentioned it. I was not explaining it to you in detail. I'll come to it tomorrow. But today my goal was to show you all the pieces in the definition. Symmetric monoidal functor between geometrically enriched cobordism and tensor algebra. So at least you have seen all ingredients. And I demonstrated you that exponential of Hamiltonian, that is Dirac quantum mechanics, is inside this construction. So 45 minutes again. Now please ask questions. So Maxim,
Yes.
you should probably ask questions.
All is clear yet, I think.
So it could not be clear because any lecturer makes 5% of wrong statements. It's an average.
I just want to think about what I hear now and create some questions later.
Very good.
I have a question at the bottom right corner of your whiteboard.
Yes.
So can you tell me why you can switch the order of L1 tilde and L2 star? It's
Because
not.
in this example, it is in this example, it's a property of tensor product in linear algebra. However, later on, I will speak about symmetric monoidal category where I can switch orders. Here I just want to show you the following thing. That the space of morphisms between monoidal products, okay, gives you monoidal product on morphism. So here we have morphisms between monoidal products. Okay? Morphisms between products. And here it's a product of morphisms. morphism of products becomes product of morphism. Interesting phenomenon, right? So now let us have a look here. Union. So here we have cobordism. And of course, I just want you to show it, that here the union of x1 and x2 is a monoidal product of morphism. Okay? But at the same time, it's a morphism between monoidal products. Okay? Once again, product of morphisms versus morphisms of products.
Professor, can you list some of the wrong statements? You just said there are 5% wrong statement. Can you list some of them?
No. You see, I only know percentage of wrong statement. So the quality of the lecturer is the percentage of right statement, or 1 minus percentage of wrong statement. So the average, so the lecturer is called good if he makes 5% of wrong statements. Because people are not machines, you know?
Okay, thank you.
So of course, since I made these wrong statements, it's hard for me to find them. So you should be able to find them. You know, when somebody is making a code, computer code, there are bugs. Okay? So bugs are inevitable. Everybody who is doing practical programming knows it. So the quality of the programmer is the amount of bugs he is doing. Okay? So the same is true for mathematician.
Sir, I have a question. Can we understand the tensor product by something such like push out? Because I think we don't talk about anything like tensor product, like something linear algebra. I guess we just need some language in category theory.
Yes, and there is such a language. This star. So people mostly use this language for monoidal structure, but this was already used. So maybe it would be better for me not to use this notation, but this notation. Then I should correct myself like this. Monoidal structure. So So here, monoidal structure would be L1. Oh, this is the bug. L1 monoidal structure L2 equals L1 times L2. So this is trivial. And here we study morphisms between monoidal products. Okay? And then here is a computation. And from this computation, I should put here this star. So morphisms between monoidal products is the monoidal product of morphism. So from this, I have the following axiom. And here is exactly the place of the bar. Because actually, in monoidal theory, you have this. So this monoidal product lies inside this space. But in the case of linear algebra, here we have equality. But in general, it's like this. So here, x1 and x2. So let me make notations. Yes, notations are fine. So morphisms between these two and these two actually contain this and this. But there are also other morphisms of such type. And if such thing happens, then here we have not isomorphism but inclusion. But it is about monoidal category. And now the last thing would be the concept of monoidal functor. So monoidal functor is something that preserves monoidal operation. Okay? Okay, so So here is a bug.
I have another question, sir. Someone asked that how to identify the boundary. I really attend the discussion place, and I have some kind like the same question. Do we consider all the objects to be manifold? And the composition to be identifying the boundary of the boundary of the manifold.
Yes. So boundary. So suppose you have a manifold. Then we say that Y is the boundary if near Y X looks like Y times this. Near Y. And here is some positive epsilon. Sorry. And we also have a cutting property. Let me take Y, middle, submanifold of real submanifold of codimension 1. Then I may consider its tubular neighborhood. So tubular neighborhood of Y middle is, of course, Y middle times minus epsilon epsilon. Okay? And then I can say that I have two pieces. That is Y middle times minus epsilon 0 interval. And here Y middle times 0 epsilon. So I am coming to this picture. And this is the process how to cut a space along closed submanifold of codimension 1. You do things like this. Okay?
Okay. And we restrict our view in the basic object is the geometric object, and can we look at all these objects like groups, and we are just identifying elements of different groups.
For what kind of groups? So the left-hand side is some geometry. So when you say groups, what do you mean?
I mean, just like I can glue like some free groups to the boundary by identifying the boundary element in the boundary group, some topological or geometrical element to some abstract element in another group. So we can get some something like not so geometrical.
You see, for some reason, I prefer to have it geometrical.
Okay.
And let me try to tell why, what is important here. In the literature, you will find a lot about cobordisms, but mostly they are related to so-called Atiyah axioms. And in Atiyah axioms, people are talking only about smooth cobordism. The so-called physics appears when you study cobordisms enriched by geometry, enriched by metric. So it is very important. So actually, I'd like to put some names on the board. Dirac and von Neumann. (1930, 1932). E to the TH. Atiyah, 1986. Smooth cobordism. Number 3, Siegel. This cobordism enriched by complex structure. And then development in this line is called Siegel quantum field theories, or some people just call it functorial. So I used to call it Dirac-Siegel. Maybe name factorial is better, because here it is something like this. It is BPZ, Белавин, Поляков, Замолодчиков. By the way, Zamolodchikov just received the breakthrough prize. The same Zamolodchikov. So they created BPZ axioms of conformal field theory. So you may try to understand these axioms in the form of special cobordism. But all these cobordisms are geometrically enriched. Okay, so not enriched. But this is geometrically enriched. Here there is a length of the interval. Here you are enriched by complex structure. So it is a very important thing. Let me tell you why it is important. Because when you enrich things with geometry, you obtain something that is called real physics. It's not just a mathematical concept. These geometrically enriched cobordisms actually observable in our world. real physics. So that's why whatever I explain today is important. Each structure.
Okay, I get it. And I remember to have another question. To the notation of e to the t times h. What do you mean? I guess is if we fix an h, we get a solution to the functor to get a functor of
Yes.
the monodal of 1 point to the category of how do I describe it?
Of linear space.
Yes, okay, to linear spaces, and every edge given functor, right? Do we
And
have some
create
restriction
a
on
function.
the edge?
Okay, there are some subtlety, and subtlety is that you see always there are subtleties. That if L is infinite dimensional, then exponential may not exist.
Okay.
So if L is finite dimensional, this is a universal solution. If L is not finite dimensional, such object may not exist. Tk h to the power k over k factorial may diverge. So in this case, people say that e to the th is actually not this. People speak about the following. About solution to this equation. So you do it like this, say, if h is where L is a function on R. In this case, such f exists and known as the heat kernel. So these are subtleties. There are some subtleties related to infinite dimensional, to the fact that L could be infinite dimensional. Equations are the same. Solution could be like this.
So do we have application for the infinite case, or in physics we only care about the finite case?
No, in physics we also care about infinite dimensional case. You just need to you just need to be precise. So when you are trying to solve this equation, you have to solve it. So it could be hit kernel equation. I think you know how to solve this equation.
Yeah, yeah.
So this equation, so you can write down the kernel x1 minus x2 square, something like t, something like 1 over square root of t with a minus. So this solves this equation. So this is an operator, and this is an integral kernel. You take this, plug it here, and check that it works. So you solve this equation, and you are done. It's an interesting subtlety, but at the first reading, you may omit this subtlety, okay? I actually wanted you to see the full picture in one lecture. And moreover, you will not find it in books. Interestingly enough, this was understood, so how long? Like 35 years ago. There are not so many people who put it in books. I mean, formulation that I give. Now I'll do what I always do. I am answering all questions. And if I say I don't know, I will just say I just don't know. Okay, now important question is, when we stop the recording, where can we find the recording? Because my students need to make notes, okay?
Someone in chat sent the link to site of course with records.
Okay, very good. By the way, Maxim, as you know, you should not make recordings.
Yes, I know.
It is forbidden to you to make this note. And you know why. You may only read it.
50-50.
Because we had an agreement that you would not spend more than 4 hours.
Could I ask the question in Russian?
Yes.